The more interesting concepts you're going to encounter when you are in computer science is DeMorgan's theorem. And it is essentially a way of reducing or simplifying a series of terms that would otherwise yield a very complex circuit requirement. So I've taken the liberty of already drawing out this circuit exactly as I have written it. And as you can see, it's quite complex. And if this were being implemented over a 64-bit architecture, then the chances that these numbers would need to be multiplied by 64 would be very high. Because whatever you do on one bit, you would probably have to do on all of the bits. You might not. You might just be operating on some flags. But you can see here we are using 4 NOT gates, 2 OR gates, and 2 AND gates. Now we want to simplify this, and simplify we shall, using DeMorgan's theorem. Now here we have taken this term here and distributed that negation to produce B and C not. Here we have taken this already distributed negative negation and we've de-distributed it. So now we have, and as you can see, the functionality of DeMorgan's theorem is that whenever you have a negation, you distribute it amongst the terms by switching their negation, and then you flip an OR into an AND, as you can see here, and you also turn the AND into an OR. And what this did, when I drew it out, was it yielded 2 NOT gates, 2 OR gates, and 1 AND gate. And that gives us 5/8 the hardware of our original implementation. We're saving money already. And again, we're using DeMorgan's theorem by doing it. But what if we wanted to take it even a step further? Because there is, in fact, a way to reduce, this original statement even better than this. And that is by doing this. We have our original statement, A, I apologize. We've already distributed the negation, so the A and B and C not, that already comes in distributed from our original, but we keep this term the same. And what we notice is, first of all, this C not is distributed between both terms. We can pull that out. And what we're left with is A and B, or A not and B not. And when you look at it a little bit, you'll notice that this is merely a negation in between the parentheses of an exclusive OR operator. This is the implementation of that equation. As you can see, we have only two NOT gates, one AND gate, and one exclusive OR gate. So that's down to 1/2 our original hardware requirement. So that is a very good savings. And here we see the logic behind this circuit. A exclusive OR B negated and with C negated. Now, in case the concept of negating an exclusive OR is completely foreign to you, I'm going to prove that it works right now. So, what we can do is start out with our exclusive OR statement, A exclusive OR B equals A B not or A not and B. And we want to show that A exclusive OR B quantity negated is equal to A B or A not B not. So why don't we take this term and negate it? So we have A B not or A not B and negated. And just to make our lives that little bit easier, why don't we put this term inside brackets and this term inside brackets, and we'll refer to this whole thing as C0. We'll refer to this as C1. Now, the reason I want to do that is because now we can say that when we go to reduce this by DeMorgan's theorem, we have C0 not or C, I do apologize, C0 not and C1 not. Actually, these parentheses can come right out. They're not necessary anymore. So when we go to plug these back in, we see we have A B not A not B not. So now we can distribute these negations throughout this term. We can distribute this negation throughout this term. And there are no higher orders of negation because we took care of that in this step. So we can dive straight in and say A not or B and, because again, no higher order of negation, so this and is preserved, A or B not. But wait a minute. If you're not having flashbacks to high school algebra, then this may be a bit of a surprise to you. But guess what we can do here? That's right, we can FOIL, just like any polynomial. So here we get, if we FOIL this, we get A not and A, or A not and B not. If we FOIL this, we find we get B and A, or B and B not. So what happens if we want to take a 1 and AND it with a 0? What's going to happen every time? It's going to be 0. So if we take a variable and AND it with its negation, it's going to be 0 every time. 0. And if we do the same over here, again, B and B not is equal to 0. Now that leaves us with this two middle terms, A not B not, or B and A. Well, that's what we wanted to prove. And just as requested, we have shown that the negation of an exclusive OR is a condition where the two input variables have to be the same. That is, they can both either be negative, or they can both either be, or they can both be 1. They can both be 0, or they can both be 1. And I'll scroll down so you can get one last look. And there you have it. Thank you and have a great day.